All right, so here's a walkthrough of how to do the problems for 6.4 related rates. I'm going to go through an example of each one of the problems. Hopefully this will help you guys work through your homework assignments in Math Excel. So we're just going to get right into it. Number one says assume x and y are functions of t. Evaluate dy dt for the following. So the first thing I want to point out with the problem that we're doing now, before we were doing dy dx, and now we're doing we're finding the derivative instead of with respect to x being down here in the bottom. You see that there's t now at the bottom. So we're taking the derivative of the function with respect to t. So that means not only when we find the derivative of y, we're going to end up with a dy dt differential being attached to it, but also when we take the derivative of x's now, we're going to have dx dt, because x is no longer the variable that we're taking the derivative with respect to. So that's very important to point out as we work through these problems. So now, for the most part, when we get to the applications, we're going to be finding a derivative with respect to time, as opposed to just the variable x in our problem. So again, when we do the derivative of both y and x, we're going to have either a dy dt attached to it or a dx dt attached to it. So now, for number one, you can see the problem here is going to look similar to yours. So let's work through the example. So we have our equation here, and we're looking for dy dt, and they give us some information here. Dx dt, the derivative of x with respect to t is 2. X is going to be 3 and y is going to be 3. But we're not going to plug in x and y or any of these values until we have taken the first derivative of the function. So now we have y cubed, and that derivative is going to be 3y squared dy dt, and then 2x squared. This derivative now, we're going to use the power rule, so we get 4x, and that decreases to 1, and then we have dx dt. Again, this is the difference for the most part between 6.3 and 6.4. We're taking the derivative with respect to time. So that's why we have dx dt after we take the derivative of x. And then 9 is still a constant, so that derivative just cancels. And now we're looking for dy dt. So now we have two options. We can solve for dy dt and get it by itself like we were doing in the examples in 6.3. However, since they've already given us all of the other information, we can go ahead now and just substitute those values into the problem and then solve for dy dt that way. So now it tells us that y is 3 from what's given in the problem. So we plug in 3 here, squared. Dy dt is what we're solving for, so we'll let that remain a variable. And then it tells us x is also 3, so we have 4 times 3. And dx dt is 2, so we're plugging in 2 for this dx dt here. And now we simplify, so we have 3 times 9, which is 27, dy dt, and then this equals 12 times 2, which is 24, and then we divide both sides by 27. We get dy dt equals 24 over 27, which equals 8 over 9 when we reduce it. And that is it for number one. All right, so here's our second problem, and it's very similar to the first. We're looking for the derivative of y with respect to t, and we've given the equation, and we're given these values. So let's go ahead and do the first derivative. So we have 3xy. The derivative of this will be another product rule situation where u is 3x and v is y. So we're going to have 3y and then dx dt for the derivative of x with respect to t, plus 3x dy dt for the derivative of y with respect to t. minus the derivative of this x is just going to be dx dt. So we'll have minus 6 dx dt. And then we'll use the power rule here, plus 6y squared dy dt. And then finally, this equals 0 because negative 84 is just a constant. So now that we have our derivative, we're going to go ahead and plug in, we're going to substitute these values into the equation. So y is negative 3, dx dt is negative 4, x is 2, dy dt is the value that we're looking for, dy dt, so that's still an unknown. We're going to solve for dy dt. And then 6 dx dt is negative 4. And then y is negative 3. So plus 6 times negative 3 squared. Watch those exponents when you're doing these steps. And then we have another dy dt that we are going to be solving for. And that all equals 0. So now let's see if we can simplify a little bit. 3 times negative 3 will be negative 9 times negative 4 will be positive 36. 3 times 2 is 6 dy dt. Negative 6 times negative 4 plus 24. And then 6 times 9 will be plus 54 dy dt. And all of this equals 0. So now we're going to combine like terms. Our constants, we're going to have 60 plus 60 dy dt equals 0. Still solving for dy dt. We will subtract 60 from both sides here. So we'll have 60 dy dt equals negative 60, and then divide both sides by 60. We'll have dy dt equals negative 1. So again, just recapping the steps. You start out with the equation. You are given some values. You find the derivative, being mindful that whenever you take the derivative of x or y, you have a dx dt or a dy dt attached to the end of it. And then after you find the derivative, you substitute the given values into your derivative equation, and then you continue solving for your unknown, which in this case was just dy dt. All right, so here's number 3. Again, it's a similar, straightforward finding a derivative problem. You find the derivative and plug everything in. So I have it written down here. First off, notice that you have 12 and ln 729 here. This, even though it makes the expression a little bit more complicated, these are constants. So when you take the derivative of these two, they will just cancel out and be 0 because they are just constant, just numbers. So now, taking the derivative here, we have another product rule, UV situation. So this will be 4 EY dx dt, taking care of just the x, and then plus 4x. And the derivative of e to the y power is just e to the y power dy dx. And then that equals, this will be 0 minus 0, so they cancel. And then we have 6, and the derivative of ln x is 1 over x. So we're going to have 6 over x times dx dt. And that'll be it for the derivative. So now we substitute our given values. So we have 4, and they tell us y is 0. So 4e to the 0 power dx dt is 9 plus 4, x is 3, e to the 0 power again. Dy dx is what we're looking for, so that's going to remain an unknown, equals 6 over 3 for x, and then dx dt again, which is 9. So now we simplify 4 times e to the 0 power. E to the 0 power is just 1. So 4 times 1 is 4 times 9 is 36, plus 4 times 3 is 12, times e to the 0 is still just going to be 12 dx, dy, this should be dy dt, 12 dy dt here, equals 6 over 3 is 2, times 9 will be 18. Now we just finish off the rest of the problem. Subtract 36 from both sides. We'll get 12 dy dt equals 18 minus 36 will be negative 18. Divide everything by 12. We will have dy dt equals negative 18 over 12, which is going to be negative 3 over 2 when we reduce it. All right, so this problem is our first application problem. It says, according to Parcell's law, the velocity of blood is given by the equation V equals K times R squared minus R squared, where capital R is the radius of the blood vessel, R is the distance of a layer of blood flow from the center of the vessel, and K is a constant. K is a constant number. A patient takes blood vessel dilation medication so that her blood velocity is modeled by the law with K equals 506.9. We want to find the rate of change of the blood velocity when R equals 0.02 millimeters and capital R is changing at 0.006 millimeters per minute. Assume that R is constant. So first thing we need to do is make sure we understand all of this information in the context of the problem. It tells us K is just a constant number. R, lowercase r, is also a constant number. So we're not treating those like variables in this situation. Even though they stand for variables in the formula, the numbers are given to us and they're telling us that we treat them like constants in the equation. So if we take the derivative of just those numbers by themselves, it's going to be 0. So it also tells us that capital R is going to be 0.02. Now capital R is a variable, so we can find the derivative of that before we end up plugging it in. And it also tells us that it's changing at a rate of 0.006 millimeters per minute, which means that dr dt is going to be 0.006 millimeters per minute when we do this part. So I have all of that written out here for the problem. So we have the equation. Again, K is a constant. They tell us that it's 506.9. They tell us capital R is 0.02 millimeters. And they tell us that R is changing at a rate of 0.006 millimeters. So we want to find it's saying find the rate of change of the blood velocity when those conditions apply. So we want to find dV dt with these conditions that are given. So before we fill it all out, let's plug in 506.9 for K, and we're going to leave lowercase r alone because it's a constant, but the value for that one is not given. So V equals 506.9 times R squared minus 506.9 times lowercase r squared. And I just distributed the 506, which was K, across this expression here. So now we're going to take the derivative dV dt of this equation. So we're going to use a power rule here. This 2 is going to come down times 506.9. 2 times 506.9 is going to be 1013.8 capital R dr dt, and we're done with the derivative because this number back here is just a constant number. So we don't need to worry about that.